It's a pleasure to be here. My name is Ricardo and I work at Talkdesk. And like Martin said, I'm here to tell you a story of how we powered up the beam using emergent technologies like Riak Core and Kubernetes. And at the same time, how we keep a balanced set of actors in a dynamic airline cluster while keeping responses under a P99 SLO of a few milliseconds. So, but first a little bit about myself. So, I'm smoking cigars, but I'm not really a smoker. It's just a special occasion. So I come from Portugal. I love to live there, and I work currently at Talkdesk for the last 3 years. And over the last 1 year and a half, I must say I started working with Elixir and Erlang, and I must say changed my way of thinking and modeling and programming applications. And I must confess it made me a better engineer, and the more I'm into it, the more I like it. So, talking about mission and goals, our mission and goals. So, our goal is to build a high scalable and fault-tolerant system that can scale, responding under a P99 SLO of a few milliseconds, so really fast. But there are many ways of doing this, so many technologies. So what help us build our system? So we need really clear features and well-established non-functional requirements. Without those, it's hard. So in essence, we wanted to build a system where we could have a very efficient way of writing and reading user state while providing a way of guaranteeing delivery of the notifications about the state changes, but with very low latency. So for the users, we need to keep serialized writes, so maintain order of events and operations, and we really only care about the last state. And we need to provide a web API for reads and writes and a subscription API for subscribe operations. In terms of non-functional requirements, like I said, low latency, we need to have P99s under 30 milliseconds for read, under 100 milliseconds for write, although we want and we think we can do better. And fault detection under 5 minutes, reaction to failure under 30 minutes, and we must, it's very important, be able to do continuous delivery. So we want to push new features, new stuff, without impacting the system or make it unavailable. So, given our mission and goals, it's why we decided to pick the beam to develop stuff on the beam. Why? Because it has a preemptive schedule, so it enables soft real-time properties, and it has a concurrency model. It's simple. It provides isolation, and it provides fault tolerance by design with supervision trees, links, and monitors. So we decided to develop our application using Elixir and take advantage of these properties. But we also used Kubernetes. Why Kubernetes here? One, I must confess it's a strategy of the company, so we want to move our services towards Kubernetes, but it also provides really cool and interesting features so that we can have these non-requirements fulfilled. Like, for example, continuous delivery, scaling, and so on. There is a bit of controversy in the community in that the Beam and Kubernetes don't play so well. And why? Because in Kubernetes, containers are ephemeral, so Beam is made to live long. And another thing, there's no hot code reloading with containers, and it's like a trademark for Erlang, so everybody starts like, oh no, it's not good. So we will introduce you some concepts, and we'll then show you how we can actually make it work and take advantage of the properties. Regarding the hot code reloading, it's also not easy to implement it. Like Fred Ebert says, it's don't drink too much cool. So, and he actually recommends that you only use it if you really need it. Otherwise, you should avoid it. So, in terms of some concepts, really small in a nutshell, Kubernetes is a platform for managing containerized workloads and services, and it uses declarative configuration. So it has a control plane that it's constantly looking to what you declare you want, and then it makes sure that this is accomplished by allocating resource and so on. So this is how it works. It provides an ingress. Ingresses are the way into your cluster, and it provides load balancing and SSL, and it can route the requests from the outside to the service. A service can be stateful or stateless. You can group. It basically can group pods for you and knows how to do this. A pod is the minimum deployment unit, and it's where your containers run, your application run. It also provides autoscaler, volumes, and operators. Operators are custom controllers that you can implement and have your own behavior to manage the resources. But without the right clustering strategy, it's not possible to obtain what you want to do, the non-functional and features we want. So it's very important to pick the right one, and this depends on your requirements. So a clustering strategy is determined for properties like fault tolerance, high availability, and scalability. So in a very simplistic way, it's the strategy that influences how processes work to do the job. So to have the job done. Sorry. So for best covering our use cases, we use the masterless clustering library, and we use Riak Core for doing it. Why? Because the main characteristics of this strategy is that it avoids choking points and contention points, has you massive scale up. Why? Because it provides, because it can slice the work in a way that is equally distributed by all the processes, and each process knows on its own how to do the job. So I must say that we started by adopting a different library, which was Swarm, but as we went to production, we got some problems, especially with the consistency of the registries and keeping that consistent. And then we decided we had to go to, we couldn't afford it, and we had to go to a plan B. So why Riak? So Riak is battle tested. It's considered a top engineering project by the community, and it has proven large-scale production deployments with success stories by Bet365, League of Legends, NHS. And it has two interesting properties for us, which is tunable levels of consistency and an API for managing the cluster. So how was our way into the Riak Core? So we had really to dig into the documentation, and it's not easy always to find the right guides, the right examples. Everything is really like scattered. And we had to ensure that we keep the same level of parity because we replaced it from the old library. And also understand what new doors it could open to your design and to our system. Understand drawbacks, like I mentioned, the documentation, the build process, it also has its own challenges. And of course, running in Kubernetes with dynamic topologies. Also integrating with Elixir, we found some small issues. And then, of course, to validate all this stuff, you had to do a POC. And with a POC, we got good results, and we decided to go for it. So what have we got? So we got an application implemented in Elixir running Kubernetes using Riak Core for clustering. The key aspects for putting this together were using LEOP cluster, how we handled Kubernetes probes and the control signals, and also using beam signal handlers. So our logical system is fairly simple. You have on the left, on the green box, you have the API, which can accept writes or read requests or subscription access requests. When you do a write, you do a publish to the broker, always in sync, and then the broker provides the subscription interface. So if you recall from features, we said we had users, and So we decided to, and we need to keep state, so we decided to model the user as a process, an Erlang process with a gen state machine, and it connects to the broker. And what it has, it's by modeling so all the operations they flow through your application till they eventually reach the process, and you do writes, reads, and subscriptions to the process. The process, because of it keeps its own mailbox. All the operations are let's say, naturally, the order of the all operations are naturally established because they are put one after the other in a mailbox, and the process reads one after the other. So you have guaranteed serialization. Also, the state of the process is always replicated on a broker, and when the process boots, it loads the state from the broker. The state is also transient, so we don't really care. We only care about the last known state. We don't want to keep the history. So we keep it always in memory. Everything is always runs in memory to be fast. So, how does this thing materializes in Kubernetes? We have these blue components, which are Kubernetes components. So the ingress makes sure you can make requests from the outside, and it knows to which service it should deliver, which is the API service. The service knows which pods pertain to the service, so it emits the request, forwards the request to one of the pods. A pod is running in a node, in an actual machine, and within the pod you have the container, the Beam container with your user processes. But then, how about fault tolerance? How about load? How do you manage this? So, to manage it, you need more than one pod, right? To manage all this stuff. And this is done how? So, you have also a component which is called the Autoscaler. It's a Kubernetes component that is always looking after your service pods for load, and it reads stuff like CPU and memory, and it's able of keeping the number of pods within certain thresholds, depending on these values. So, when you need it, a new pod comes in green, for example, like it's in the illustration. But so the service has a new point of contact, but it's still red. Why is it red? Because there's also another component, which is the probes. So Kubernetes also has the probes concept, and these probes keep checking your application to see if it's alive and ready. So it's up to your application to tell if it's ready to accept traffic and so on. So based on this, when the application declares it is ready, the service will be able to forward requests to both pods. So, but then there's also a problem. What is the problem? The pods don't see each other, so they are not aware of each other. And what is the consequence? The consequence of this? So when two requests come from the same user, if they land in different pods, you will create two different user processes, and you break the serialized order of operations. Also, if pod 1 was loaded and you bring out a new pod to, if it's loaded, I need a new pod to balance work, pod 1 will continue loaded, right? Because it wouldn't help. So only for new requests. So we need clustering, and that's what Riak gives us. So in a nutshell, Riak uses consistent hashing. It divides the space into equal parts and parts, which it calls vnodes, and given a key, it hashes it, and it's able to find one partition, which is a vnode. So in our particular implementation, we use the user ID as the key, and so when you hash it, you can fit the users into vnode slots, and with this you distribute all your users through the vnodes. So if vnodes are split, users are also split. Additionally, Riak makes sure that all the vnodes are balanced within the cluster. So each pod has, or each application has the same amount of vnodes spread. But there's an issue here. There's always issues. Is that Riak Core doesn't support auto clustering. So how do we do this? So when you scale up, we do it with LEOP cluster to help manage this. So LEOP cluster, as you can see, it runs in the container, in the beam, together with Riak Core application. So how does it work? So it keeps polling the Kubernetes API, and it asks Riak Core. So it polls Kubernetes API to see what pods are there, what are the real nodes, and so it's a source of truth, and then it asks Riak Core what you think it's your cluster. So in case these two do not match, what happens? So when Kubernetes says, I have one more pod than what Riak thinks, it means that you have one new one new container, one new application that you need to join the cluster. So it provides hooks where you can configure, and you say, when a new pod comes in, it calls Riak Core to join this new pod to the cluster. So what happens now? Now we have a cluster. So vnodes are rebalanced, and the load is also rebalanced, and you maintain one user process, and it can be you can keep the order. But at the same time, there's one thing missing, which is the scale down. How do we scale down? Well, scale down can happen in two situations. You have two situations. So I was saying you can have an abnormal case where something really wrong happens, like a node just collapses or it just deleted. The machine stops working, and then you have the case where you gracefully shut down. So this can happen when you do a relocation of a pod of one place to another, or the autoscaler determines that, oh, you have few requests, so I don't need so many pods, so I reduce the number of pods doing the service. So how do we handle abnormal scale down? So it's very similar to the join. So you keep matching what Kubernetes tells you and what Riak tells you. So if Kubernetes tells you are one pod down, so you need to adjust Riak cluster. And how do you do this? You call the force remove Riak Core API. The cluster will call this, and it will remove the node from Riak, and the order will be established. So the ring will be as it should. For the graceful shutdown, we need to implement a signal handler that runs on the beam. Why? Because when Kubernetes wants to shut down a pod, it sends you a signal, a sig term. If you don't do anything, the application just disappears, and it's like an abnormal termination. It would be like that. So when you handle the signal, you implement this signal handler. It's initially in a serving state, and in a serving state, there it's green. It means that when the probes are contacting your application, you are saying, okay, I'm ready. You can continue sending requests. But as soon as you get the sig term, you go to a draining mode where you start saying the probe that I don't accept more traffic, so that no new requests come to you. And you wait a draining timeout to give time for the probes to act. And after that timeout, you enter a shutdown period where you still wait for pending connections to terminate in case you shouldn't have, or if you have a few, but you still wait for it to guarantee there's nothing, and then you invoke the leave API, which is the graceful shutdown of the Riak, and you exit the cluster, and this pod will exit the cluster normally, and it will be good. So now what we have our API system right on the left with auto clustering, with the vnodes and the users balanced, and we provide also a subscription interface on the right via the broker. So what happens when you have a subscription request? So the subscription request there in green will come in. Subscription access will come in through the web. It will go to the ingress. The ingress will know you want to access the API service that is on the left. and then the service knows which pods it belongs. These are the 2 pods. It picks one randomly. In this case, it hits the first on the top, and we will ask Riak Core API, where is this process? Where is the and it says, oh, it's in the other node. So Riak Core will forward the request to the other node, and you will get the answer back. Then the client, because he wanted a subscribe access, it will come again to the ingress, but now it will go to the service side of the broker, which knows it has 2 pods. Here it's indifferent if you pick one or the other, because user state is replicated between the brokers. So it will go to one broker and it will establish the connection. So that's how we did it. So, and conclusion, so goals and requirements are really essential to make decisions about the technology to use and about the design of a system. Without it, you can do many things, but this is what determines what you pick and if it's right. Then production is really the true test. So you always find new stuff, and only after running days, weeks, you can say that it's good. And with Riak Core and Kubernetes, we can power up the beam to be capable of keeping a balanced set of actors with a dynamic Erlang cluster. And we can be fast and respond under a P99 SLO of few milliseconds as you scale. But we are not happy yet. We believe we can do some improvements, and we can be faster, and we also have ideas about them. And basically we can achieve higher levels of ability at the cost of some consistency. So we can use user process replication, for example, 3. And with that, we would need to use a strict quorum with primary rights. Primary is greater than n, so that we can continue can establish the right order. The broker, we have to change a little the architecture of the broker, so the broker would have to serve only the nodes Riak vnode space, so it would have to be attached kind of to the API node, and we could add vnode worker pools. Why? Because the vnode handles users, and as the vnode handles more and more and more users, because we are using sync commands, it can be a contention point, and by using vnode pools, you can get out of it and be fast. Don't block there. We should also transfer the user's process state when rebalancing. This would avoid at boot loading the state from the broker, and it would be faster. We could save this step. And then to finish, better auto clustering. So we could try to implement a controller, which is, we call it Riak operator, and this controller, it's custom. It will take advantage of stateful sets, and we could use Riak Core replace node API. So this will make it easy, the process of rollout and the process of scaling up, because you don't need to, when you add a node, we are basically shifting all the vnodes, and then you delete the old node as you roll out. So everything is shifted again in the cluster. So the distribution keeps shifting a lot between all nodes, and you just want to replace one with the other. So you should only shift vnodes between those nodes. So this will decrease the entropy in the system when you do this. Okay, so that's what I wanted to present. I hope you enjoyed.
Thank you very much, Ricardo. And right now we have a coffee break outside, so I guess you'll have to do the Q&A outside.
Yeah,
yes.
Sure.
Thank you.